Let's go over the test for Unit 2. So the first problem is we need to factor this, which means we need to know its zeros or roots, their multiplicity, and their behavior at those roots, the function's behavior at those roots. Is it going straight through or at an angle or something? Hopefully my battery's not too low here. And I've typed in the equation. Well, not quite. Let's see. No, this is a different equation. So let's clear this one. It's negative x to the fifth minus 3x to the fourth plus 2x to the third plus 7x squared. Oop, didn't hit the push over. Get up, stay up there. 3x to the fourth plus 2x to the third, get over, plus 7x squared minus 3x, subtract by minus 2 or subtract 2. Okay, if I've got this in, and I'm going to double check here because that's where many students have trouble, is not getting it in correctly, and it looks pretty good. I'm going to go zoom 4. Hopefully all the roots are between negative 5 and 5, and I see 1, 2, 3, 4, 5. The bounce is a double, straight through, straight through, straight through, bounce. That's the behavior. So looks like there's one at, somewhere between -2 and -3. That's not a very nice place. I'd like it to be nicer numbers. There looks like there's one at -2. That looks like a nice one, so I'm going to write that one down. I'm going to find this other one between -3 and -2 by going second, calculate the zero between, and I'm typing in -3, enter, and -2, enter, and my guess is going to be -2.5, and it says it's -2.618 something. I'm going to just write this down on the side here, -2.618 something. Doesn't look like it's repeating, which would it have to be a fraction. So I don't think that's a fraction. So, but the one over here at -2, let's just trace. Let's just move along. Trace. Move along, and it looks like, yes, at -2 it's 0, so that is a 0. And it looks like we got another one that's not a nice number here. It's missing it. Something between -1 and 0. Notice I have to go from left to right when I do this on the calculator. Second, calculate the 0 between -1 and 0. And I'm going to put it in as -0.5, and it'll correct me here. It says this one is -0.3819382-ish. Again, it doesn't look like it's repeating. I don't think it's going to go 66666 there at the end. So I don't think that's a very nice one. So I want to get the exact ones because I'm going for the bonus, so I'm going to leave that one off to the side. But the next one looks like if I keep tracing, it looks like I got 1 at 1, and it says, say, 1. Now, at 1, it's bouncing off the x-axis. That tells me that the multiplicity is 2 because it bounced. And at minus 2, it went straight through, so it tells me that it's a single root, multiplicity 1. Now you don't have to put the m's, but that's what I'm saying here. So that's how I'm determining these. Well, that's a total of 3 zeros. Since it's degree 5, it has 5 potential zeros. Some of them may be imaginary, but I had these two and this one twice and this one. That's all 5, so I know that I can take this degree 5 by doing synthetic division by this number once and this number twice. I can get it down to a degree 2 or a quadratic, and I can use the formula, quadratic formula, and get these roots exact. So that's what I'm going to do now. So to do synthetic division, I write the coefficients in decreasing power of x's, and so I'm going to make sure I have all the powers. X to the 5th, x to the 4th, x to the 3rd, x to the 2nd, x to the 1st, and no x, so I have them all. There's not an x in common, so I can't pull that out. I didn't get a 0 for a root, which would mean I could pull an x out, so I'm going to write down, I have -1, -3, 2, 7, -3, -2. And I can start with the -2. I like the ones better, so I'm going to use 1. I'm going to do it twice. Here's the first time. -1 plus nothing, so you always add down, and I get -1. Then you multiply to get the next one here. 1 times -1 is -1. If I add down, I get -4. Multiply this way, and I get -4. Always add down, and that adds up to be -2. Multiply, and I get -2. Add down, and I get 5. Multiply, and I get 5. Add, and I get 2. Multiply, 2, add, 0. It went in evenly, so I know that it for sure is a 0. And I think it goes in twice because of the multiplicity, because it bounced. So I'm going to try to put it into what's left, factor this. So add down, -1 plus nothing is -1. Multiply, add, multiply, add, multiply, add, multiply, add. We came up with 0 again. So it for sure is a double root. And I went from degree 5 to degree 4. This was x to the 5th, x to the 4th. This is x to the 3rd. It's almost a quadratic where I can use the quadratic formula. Not quite. But fortunately, I know one more 0. We hope -2 should go in evenly. Add down, -1 plus nothing is -1. -2 times -1 is +2. Add, I get -3. -2 times -3 is +6. Add, I get -1. -2 times -1 is 2. Add, and I get 0. It went in evenly. And now I've gone down to an x squared minus 3x minus 1. Now I have a quadratic, and I can use the quadratic formula to get these two decimal approximations in exact form. Now before I do it, I notice that each one of these has a minus, so I'm going to factor out a minus 1, and then it would be x squared plus 3x plus 1. If I had a 2 in all of them, I'd factor out a 2. If there's something to factor out, let's make it easier on ourselves. So, quadratic formula, I need to know what a is. And there's 1x squared. Now, if you left it minus in there, it would have been minus 1. B would have been minus 3, but now that I factored out is 3. And C could have been minus 1, but it's going to be plus 1 because I factored out the minus 1. Quadratic formula says the opposite of B, so that would be negative 3 plus or minus the square root of b squared, so 3 squared is 9, minus 4 times 1 is minus 4. All of this is over 2 times a. This part's over 2 times a, which is 2, and this part's over 2 times a, which is 2. So I have negative 3 halves plus 9 minus 4 is 5, square root of 5 over 2, and minus 3 halves minus square root of 5 over 2. If you type this into your calculator, you'll get that decimal. If you type this into your calculator, you'll get that decimal. So now I know the last two roots exactly. Minus 3 halves plus the square root of 5 over 2. It happened once. It went straight through at that place. So the multiplicity is 1. And it went straight through. And the other one was at minus 3 halves minus the square root of 5 over 2. Multiplicity 1 because it went straight through the x-axis on the graph. And there wasn't any more zeros. There's 1, 2, 3, 4. And this one's a double, 5. There's all 5. So what is the factored form? Well, the factored form is, see, I factored out a minus 1. So I have minus 1. And then I have, if minus 2 is a root, x plus 2 has to be a factor because minus 2 plus 2 would be 0, causing it to be a 0 or root. So, and if 1 is a root or 0, it must be x minus 1 because 1 minus 1 would be 0. And if its multiplicity is 2, I have to have it twice, so I'm just going to put a square on it saying it's twice. I could also write it twice. Then I have this one. So that's going to be x, and if this is the 0, and I put that in for x, I have to have stuff that would cancel that. So it would have to be plus 3 halves minus the square root of 5 over 2. And finally, if I had put this in for the x, it would have to have a plus 3 halves plus square root of 5 over 2. So there's the factored form of f of x. The original function. This factors to this. If I were to carefully FOIL all this all together, I should be able to get back to that. Okay. Intercepts. Some of you are going to complain bitterly, but intercepts are where they cross on a graph where the curve crosses the y-axis or the x-axis. Those are points, and points have coordinates. So the y-intercept should be given as a point. And to find the y-intercept, if you're on the y-axis, x is 0. So you can put 0 in for all the x's, and whatever this works out to be is the y-intercept. So you're putting in 0 for the x, and if you put 0 here and here and here and here and here, all of that would be 0, and we're left with minus 2. And you can see that on the graph that it crosses the y at minus 2. The x-intercepts are, well, it's the numbers that make zeros. A minus 2 makes this be 0. A minus 2, so it's minus 2 makes the y be 0. That's this point at its negative 2 and 0 high. X-intercepts. X-intercepts are always the zeros or roots, and the y height has to be 0 to be a 0. That's the whole point of it. 1, 0. It happens twice, so I only have one x-intercept for that one. And then I have negative 3 halves plus the square root of 5 over 2, 0, which was this number. A lot of you use the decimal version. You miss some extra points for not using it. And then the other one was minus 3 halves minus the square root of 5 over 2, 0. The end behavior, that's wanting me to talk about what happens as where does the graph go as we go further to the left or to the right? Well, the left end behavior, the curve is headed towards positive infinity. So left end behavior is headed towards positive infinity. And on the right side, what's going there? Well, the graph is headed towards negative infinity. It's headed down. Okay? That's what I mean by end behavior. That's what's meant by end behavior, I should say. Determine local maximums. Local means in their neighborhood. If you don't move very far, is there a place where it's the highest in its neighborhood? Well, you can see here that this is going up and coming down. There's going to be a high spot there near that spot. There's a high spot, and that's called the maximum. And we want to know how high that is. And on the calculator, we go, let's see, that's a good spot for it. That looks like it happens somewhere between negative 2 and 0. So I'm going to go second trace, or second calculate, the maximum. That's between, so I'm going to say between negative 2, enter, and 0, enter, and looks like it's near negative 1. Negative 1 is good enough for a guess, and it says the maximum happens at this value, but that's the maximum. So the local maximum is 4.509. That's a local maximum. Now, for further problems down here, it's good to know where it happened at. At x equal negative 1.244. Negative 1.244. That's where it happened, but the maximum is how high it was. So this graph came down. There's a low spot here. That would be a local minimum. Then it has a local maximum in this area. That's a high spot. Has a low spot here, another local minimum, and another local maximum right there. And it looks like the height is 0. In fact, since at 1 is a 0 and it bounces off, we know that maximum is 0, and it happens at 1. Now that's not the maximum. It's where it happens, at x equal 1. So I'm keeping track of where. That's not important for the answer here. The maximums are this one and that one, local maximums. Now let's do the local minimums. This one appears to be between x minus 3 and x minus 2. So I'm going to go second, trace, and calculate the minimum. That's between the x value minus 3, enter, and the x value of minus 2, enter. And I'm going to make a rough guess of minus 2.5. That's between minus 3 and minus 2. And it says, no, it happens at negative 2.36. But what we want is the minimum. How low did it get? And it got down to negative 2.074. Negative 2.074. But for purposes down here, I'm going to keep track of where it's at. Not necessary for this answer. And this is at x equal negative 2.360. Negative. And there's another minimum right there that's happening between x equals 0 and x equal 1. So second, calculate the minimum that's between 0 and 1. It's somewhere between there, and it looks like it's about 0.2, and it says it's 0.204, but the minimum, the height, which is what the minimum is negative 2.309. Negative 2.309. Now, like I said, I'm going to keep track of where it's at. X equal 0.204. But this is the local max, a min. That's a local min. That's a local max. That's a local max. Don't need these parts for this. But for this, I might need it. Or for this one. Interval where the height, f is, remember, is the height. So intervals we talk about for what x's. When I ask for intervals, when a mathematician asks for intervals, we want to know for what x's is the y, the f, above 0 or equal to 0. Well, this graph is above the x-axis. It's above 0, below 0, above 0, and it goes down below 0, and it gets up to, touches 0, and then goes down. So when is it greater than or equal to 0? Well, it's greater than 0 all the way up to that 0. So for x's, again, we talked about the intervals. As long as x is down here, we know this graph keeps going up, and so it's always positive. So for x's from negative infinity all the way up to that 0, the height of the graph, the y values, are greater than or equal to 0. So from negative infinity x being negative infinity all the way up to that 0. And that 0 was, let's be exact here, negative 3 over 2 minus square root of 5 over 2. Up to that point exactly, it's greater than 0. At that point, it is 0. Since I said, yes, keep it equal to 0, because I got an equal sign, I'll put including that point. So from there to there, for all these x's, the y height is greater than 0. Then the y height dips down, so I don't want any of those. But it's greater than 0 in another place, so we have to connect these with the next place by saying union, and the next place looks like it starts at negative 2 where it was 0. At negative 2 it was 0, so I'm going to include the negative 2, include, not a parenthesis, negative 2, and when does it quit being above 0? Positive value. And it quits when it crosses at that not so nice number, which was negative 3.382, or this root, negative 3 halves plus the square root of 5 over 2. So it was above 0 here for all these x's, then it wasn't for those x's, then for these x's it is greater than 0. For these x's it's not greater than or equal to 0. And here it is equal to 0 only at that point. So if we're going to do interval notation, we would say from 1 to 1. That means starting at 1 and ending at 1, we want to keep it. Well, that's the only place there is at from 1 to 1. There's no space in between them, so it's just that place at 1. Those are the three intervals, the three sections of the graph where the y height is greater than 0 and not less than 0. Y height is greater than 0 for those x's, not these and not these, but at 1 also. Now, again, if I'm doing intervals and want to know when the function is increasing, that means as I go from left to right, it's going up. It's getting higher. It starts where it's the low spot and ends at the high spot. Now, at the low spot, it's changing from decreasing, coming down, to increasing. So I want to start at the low spot, but not, it's changing there, so I can't include it. So that's why this one is open parenthesis. And that low spot, here's why it's good to keep these. This low spot of negative 2 happens at x equal negative 2.360. So that's where I'm going to start my low spot, negative 2.360. Starting at that x value over to the x value where it's the highest, it's increasing. Now where it's highest right here, this local maximum was 4.509, but the x value is what we want. For what x is it increasing? It's increasing from negative 2.360 as we go over to negative 1.244. That's the x value for that maximum. That's why I kept these numbers. So it's increasing from this low spot to that high spot, from that local minimum to that local maximum. And at this place, it's changing from increasing to decreasing, so I don't want to keep it. Now it's decreasing all the way through here, so I don't want any of that, but it's increasing again here, so I want to get those. So I'm going to go union, connect those, add these possible x's to that, And so we want to know what the x value is at this low spot. That's a minimum. That's the minimum, but the x value is 2.204. And it keeps increasing until the x gets to be 1. At 1, it's changing from increasing to decreasing, so we don't want to include it. And that's page 1 of the test.